Alright, how's it going, everyone? Hope you're having a good day. Today we'll be looking at the review for the third test. So, does anyone have any questions before we get started? Okay. Alright. So, looking at the review. Problem 1. General Electric manufactures a decorative, crystal clear 60-watt light bulb that it advertises will last 1,500 hours. Suppose the lifetimes of the bulbs are normally distributed with a mean of 1,550 hours and a standard deviation of 57 hours. So what is the probability that a light bulb will last less than 1,500 hours? Well, first of all, let's pick out some key details here. See, the mean is 1,550 hours. Standard deviation is 57. And then we want the probability that the bulb will last less than 1,500 hours. And that's really the key information that we need right there, looking at that problem. So we have our mean is 1,550. Standard deviation is 57. And we want the probability that it would last less than 1,500 hours. And that's our data value, x. By the way, when I created the test, you probably, at least in this class, you probably saw that I updated the test yesterday. So that's ready to go whenever we finish today. You can start to take it if you want to do it before Thanksgiving, or you can wait till after if you prefer. What I've done is on the first 5 problems, I've made them multiple choice, and what I encourage you to do there is if you don't get some of those problems right, be sure to scan or take a picture of your work and send that in to me. That way I can give you partial credit for the work that you did. And it may just be one little error that you had that caused it to be incorrect. So don't worry about so go ahead and email me all that work, and you know, you can email me your work for the entire test. The last 3 problems will be a series of fill in the blank, and we'll talk about that when we get to those 3 problems. So, anyway, now if you get these first 5 problems right, then you don't have to worry about sending in your work, or the other 3 for that matter. But you definitely do that, and I can give you some partial credit. I don't know. Does it tell you which problems you got wrong, or just your grade when you finish? I think it tells you which problems you get wrong, but not necessarily what the correct answer was yet. Anyway, but correct me if I'm wrong. So we use our z-score formula here. Z equals x minus mu divided by sigma. X we know is 1500. Mu is 1550. And sigma 57. So we will subtract on top and then divide by 57. That comes out, and we'll round to 2 decimal places here. Negative 0.88. Okay. Okay, good. That's what I suspected, but I appreciate the confirmation there. I don't always see it from, I'm not able to look at it from the same point of view that you all do, unfortunately. Alright, so we get our z-score. Which is a negative, so 0 being in the middle, negative 0.88 is over here. And we said less than 1500 hours, that means we'll shade to the left. Less than is to the left. So this is the area that we're trying to find that represents this probability. Now, we look at our bounds. Our lower bound, as it continues to the left, we'll say negative 10. And our upper bound is just the right boundary here, negative 0.88. Okay. And we'll just put those into our calculator and go from there. So this calculator, we go second data, distribution, normal CDF, 0 and 1 for the mean and the standard deviation always. And then our lower bound is negative 10, upper is negative 0.88. Calculate. So it gives us a value of 0.1894. Okay. Part of why I decided to make these first couple of problems, especially multiple choice, is that they're relatively short, and as long as we've done everything correctly, it's pretty easy to, I'm not gonna say pretty easy. The approach is generally straightforward. But it's relatively short problem, so you'll know if you get the answer or not. If you've done it absolutely correctly, you should get exactly the number. There's going to be 4 options, so you should get exactly the number, and there won't be anything real close to it. So if you're a little bit off, or if you did round it a little bit differently here for z, you should still be able to pick out the right answer for that. So the numbers are not going to be so close together as like you're going to drive yourself crazy. I don't want to do that to you. Anyway, continuing on, number 2. Oops, there we go. What is the probability a light bulb will last between 1500 and 1650 hours? Now, we're still referencing the same question, in the Canvas quiz I've repeated the header that went with the first one so that you do, or there's no confusion as far as what data we're using. But we'll use the same mean and standard deviation as before. And we want the probability that the light bulb will last between 1500 and 1650 hours. Now, when they give us two numbers like this, these are both x values. Okay. So that means whenever it's between, like we have here, we have to find a z-score for both of the values that we're given. So for x equals 1500, we have to find z. And we can use the z-score formula, x minus mu over sigma. However, you may notice that 1500 is exactly the value we used in number 1, and we already have its z-score. It's negative 0.88. So we don't have to do that a second time. Now we do need to calculate the z-score for 1650 because we haven't done that yet. So z will equal our x 1650 minus mu 1550 over sigma 57. Subtracting, that's 100 divided by 57. And we'll round that to 1.75. Again, 2 decimal places for z-scores always. And already we can see right here our two boundaries on our shaded area. Anytime it's between, it's just those two numbers. But drawing up our curve, negative 0.88 is to the left. 1.75 is further to the right. Again, this part doesn't have to be perfect. This is just for illustrative purposes, what it is that we're looking at. It looks like a pretty significant area, so we should get a relatively large number here. So our lower bound is negative 0.88 and our upper 1.75. Okay, so we'll put that into the calculator. Zero one, lower bound negative 0.88, upper bound 1.75. Calculate. So you get 0.7705. And so that's the probability that the light bulb will last somewhere between 1500 and 1650 hours. Okay. So, in those first two problems, fairly cut and dry. Moving on to problem 3. The number of chocolate chips in an 18-ounce bag of Chips Ahoy chocolate chip cookies is normally distributed with the population mean of 1,682 chips and a population standard deviation of 118 chips, according to a 1999 study. Determine the 90th percentile for the number of chocolate chips in an 18-ounce bag. Now, there's a few extra numbers here that we don't want to be distracted by. The size of this bag of cookies, 18 ounce, we don't use that number. We don't use the year either. We see these numbers here, but they're not significant. It's really just for the context of the problem that we have them. So the main things we need are the population mean, 1262, and the standard deviation, 118. And we want the 90th percentile. Those three things are really the information that we need from this paragraph. So go ahead and write those down. And that's really the biggest thing right there, is picking out key data from this description of the study. Now, whenever we want to find the number of chocolate chips, the 90th percentile for the number of chocolate chips in an 18-ounce bag of cookies like we have here, anytime we're finding percentile, we're using the inverse normal function. Basically reversing the normal CDF function. And our area, in this case, will be 0.90, representing 90%. Most of the work here is done in the calculator. The second data, distributions, and we see our third let me get my head out of the way. See, our third option is inverse normal there. So press enter and go in and say area. So we say 0.90 is our area. We fill in our mean, which we said, I moved the whole thing down. Our mean is 1262. And our sigma, that's our standard deviation, is 118. Enter and calculate. And so it gives us a value of 1,413, and it's 0.2. So we'll just round that to 1,413 chocolate chips. Okay. It's kind of an empty space left by my calculator there. Anyway, so we are able to find a 90th percentile. That means if we happen upon a bag of cookies where it had 90%, it had more chocolate chips than 90% of the other bags, it would have 1,413 chocolate chips, where the normal value is 1262. So if you're a chocolate chip fan, that's a good deal if you get that 90 percentile bag. I don't eat a lot of chocolate chip cookies. Yes, absolutely, Haley. Do you have the 83 or the 36? We can look in either one or both. So we go to second data. Arrow right to distribution. You know, most of our problems we're choosing normal CDF anytime we have a z-score. This time we do not have a z-score, we have a percentile. So we go to our third option, inverse normal. Press enter. And then for area, if we have a 90th percentile, we'll put 0.9 there. Okay. So whatever percentile it gives us, we'll enter the appropriate number in decimal form for the area. Now specifically, this is area to the left. I'm not going to try to trick you though. The number I give you will just be a percentile, which percentile is always area to the left unless it says otherwise. So, and I'm like I said, that's exactly what I'm going to give you there. It's not going to be a trick question or anything. So enter 0.9 And then our mean, standard deviation, those are already in there now. Go down to calculate, and it gives us our value. And so for this number, since we're talking about the number of chocolate chips in a bag of cookies, we can go ahead and just round that to a whole number. Although the presence of partial chocolate chips is not out of the question. Unlike light bulbs. Is that alright? Moving ahead to number 4, I never remember why I put that on the page by itself. It's the shortest problem on the test as far as the amount of writing goes. Anyway, at least it didn't waste paper, it's all digital. Suppose that a local doctor studied the pregnancies of a random sample of 36 of her patients from the past year. The population mean for the length of pregnancies is known to be 266 days, with a standard deviation of 16 days. So for problem 4, what is the probability that the average length of pregnancy for the sample is less than 270 days? Now, an important thing for us to notice here is that we have a sample size of 36, and that's going to impact which formula we choose for z. We also know that the mean is 266 and the standard deviation is 16. And then we want the probability, the average length of pregnancy is less than 270 days. That's all of our key data. There's really no superfluous data in this case, but that's always nice when that's true. Okay. So we know our mean, or it's actually our sample size is the first thing we're given, n is 36. Our mean, mu, is 266. And our standard deviation is 16. And we want the probability, the average length of pregnancy is less than 270 days. Which is a pretty reasonable assertion because very likely the average length of pregnancy is going to be right near 266, so that it's less than 270 is pretty likely. So we should get a relatively high number here, just thinking about it. Especially when we have a sample size like this. Now, that's our x bar value now. Now, the reason we know this is x bar is the sample mean. Remember, the question says that the average length of pregnancy for the sample is less than 270. So the average is x bar, okay, the mean. Specifically for the sample. Now our z-score formula, in this case, utilizes the sample size n. Technically, the sample size modifies specifically the standard deviation, but again, this is what I call the more user-friendly version of this formula, which actually brings up the root n to the numerator. So we plug in all of our values. We have the square root of 36, 270 minus 266. And then 16 on the denominator. Okay. And so that'll give us square root of 36 is just 6. 270 minus 266 is 4. There's 16 on the bottom, so it's 24 over 16. Which is like 1.5. Let me verify that though. Yeah, 1.5. So that'll be our z-score in this case. Okay. So we have z is 1.5, and we remember that we said less than 270 days, so it'll be to the left of 1.5 on our graph. Now 1.5 is to the right because it is positive, and so we want to shade everything to the left of that. Now it continues all the way to the left, so our lower bound is -10, and our upper bound is 1.5. So we put that into our calculator. Now this time we're back to using normal CDF, so we'll just arrow down to that. One thing I want to point out here, especially after we've done problem 3, notice the mean and the standard deviation here are still the values from problem 3, so we have to change it back to 0 and 1. We always want to use 0 and 1 here because we've changed it to a z-score, and these are the mean and the standard deviation for the z distribution. So anytime we're doing a normal CDF, we should be using 0 and 1 as kind of our converted mean and standard deviation. Now, here we're going to enter our lower and upper as normal, -10, 1.5, and calculate. So we get a pretty large number, 0.9332 after we round. So better than 93% chance that the average length of pregnancy in this sample is going to be less than 270 days. Okay. Problem 5 follows that. It says, what's the probability that the average length of pregnancy for the sample is greater than 260? Well, we just repeat the whole process, but now we do greater than 260 instead of less than 270. So it's almost exactly the same. Flip this over. So we have the same information. N is still 36. Mu is still 266. And sigma is still 16. And again, for this problem on the test, I just copy and pasted the description of the problem, so you know, just so there's no confusion about what data we're using for this. We want the probability that it's greater than the sample mean is greater than 260 days. There we go. So 260 is x bar. Anyway, so we calculate our z-score. Square root of 36, and then 260 for x bar first. Mean is always second, subtracted. And 16 on the bottom for the standard deviation. So we get the square root of 36 is 6. 216 minus 266 is negative 6. And we have a 16 on the bottom. Negative 36 over 16. It's like 2.25. Let me double check. Negative 36 divided by 16. Yes. Negative 2.25. Okay. My graphs are not as symmetric as they need to be. Negative 2.25 is way over here. Generally our scale that we have for these is about negative 3 to 3. So I try to draw my lines accordingly based on that. But again, it doesn't have to be perfect. As long as we get it on the correct side, we have a general idea of what we're looking at, we should be fine. But greater than would be to the right. So we're going to have a probably even larger number here than we had in number 4. Our lower bound is negative 2.25, and our upper will just go all the way to positive 10. Go down the normal CDF. Negative 2.25 is our lower. 10 is our upper. Well, I just screwed that up. Sorry, I got distracted. Let me start over. Quit and repeat. 0, 1. Now we have negative 2.25 and 10. Calculate. Yeah, 0.9878. Very large chance that for a sample of 36 individuals, the average length of pregnancy will be at least 260 days. Almost 99% probability. Okay. So those first 5 problems, like I said, will be multiple choice, but again, if you do get them wrong, be sure to send me your work through email or Canvas, just so I can give you credit for partial credit for the work that you've done. And it may just be that you had one little mistake that led you to the wrong answer, and I can give you most of the points back in that scenario. Anyway, now the last 3 problems will be, as I said, just a series of fill-in-the-blank answers. So they're all, it's not like drop-down menus or anything. It's just fill-in-the-blank is really all it is. So whatever values I asked for, I'll be sure to prompt you for those. So problem 6, it is believed that 30% of Americans believe, I probably could have written that more professionally. It's believed that 30% of Americans believe that places can be haunted. Suppose that 205 college students are surveyed as to whether they believe places can be haunted, and 65 responded with yes. Find the following. Okay, before we dive into this problem, again, we want to write down our key words there, or key values. Key values is a better way of saying that. Let me start with a fresh sheet of paper. So, 30% of Americans believe that places can be haunted. So that's our proportion, population proportion, P. And we'll express 30% as a decimal. 205 college students are surveyed. That's our sample size N. And 65 responded with yes in this survey. And so that is our X. Okay. First thing we want to do here is A, show that the distribution is approximately normally distributed. Put this up here. Okay. Now, to show that it's approximately normally distributed, we have to demonstrate n times p times 1 minus p is greater than or equal to 10. So in this case, I will prompt you for the value of n times p times 1 minus p, and then it should be greater than 10. Okay, so n is 205, p is 0.30, and then 1 minus 0.30. So it's 205 times 0.30 times 0.70. And you can write 0.3 and 0.7, it's the same thing. But we'll go ahead and multiply those together. So 205 times 0.3 times 0.7. So it gives us 43.05. And that is greater than or equal to 10. Okay. All right. For our part B, we want to find p hat, which on the test I've referred to as p hat because I don't know the keyboard shortcut to put the hat on the letter P. Anyway, I could have looked it up, but I was kind of in a rush when I was putting the test together. Anyway, I was more focused on the answers being correct than anything else. So p hat is just x divided by n. That's our formula. And as you see, let me show you the formula sheet for proportions. This is at the top of your test when you go into it. Sample proportion p hat is x over n. The condition for approximately normal, n times p times 1 minus p is greater than or equal to 10. We also have the formula for the standard deviation and the z-score, which are coming up here in a second. But this is all provided to you on the header of the test, basically. Let me go back to the problem now. There we go. Alright. So x over n, that is 65 divided by 205. And we get 0.317. So we'll use that for p hat. On the exam, again, I'll specifically say round this number to 3 decimal places when you fill in the blank. So just so that there's no confusion. And that's what the test is going to be checking this number on. So when you put in your number in the blank, again, make sure there's no spaces. You can put a 0 in front or not. It actually doesn't care which way you enter the 0 here. As long as you have 0.317, that's what it's going to be checking, or whatever the number comes out to be. Hopefully by now, most of you have. I think most of you do have the hang of it by now. After the last couple of tests, well, specifically the last one, we didn't really do that too much in the first one, although there was a little bit of it, I think. Anyway. Alright, so in part C, we want to find the standard deviation and calculate the z-score, and then find the probability that p hat is greater than 0.317. Now our standard deviation, sigma p, is square root of p times 1 minus p over n. Now, p is 0.3, 1 minus p is 0.7, as we already discovered, and n is 205. So we just need to calculate that, and we'll be okay. So we have square root 0.3 times 0.7. Back up a bit there. Didn't hit the 3 hard enough. There we go. That's why I keep looking over at the screen so I can see it better. 205, close parentheses, enter. Oops. And this is 0.032. Now this number, I will say round to 4 decimal places on the exam. I believe I said 4. This one, our fourth character is 0. Actually, our fourth and our fifth are 0, so it's just going to be a 0 there. Anyway, so just make sure you follow the instructions, and it should work out okay. So we have that, and finally we have a probability question that we want to answer. Probability that p hat is greater than the value in part B, 0.317. Okay. So our z-score is p hat minus p over sigma p. So we'll put in 0.317 minus 0.30 for p, and sigma p was 0.0320. Alright, and so dividing, or carrying out that arithmetic, we end up with 0.53 for a z-score. So far, I'll have you fill in a blank for np times 1 minus p, which is 43.05. Fill in a blank for p hat. Fill in a blank for sigma p. Fill in the blank for z. And then finally, fill in a blank for the actual probability. And to calculate the probability, now we're back to, this is not a great normal curve. 0.53, and we said greater than that, so it's actually the area to the right. So our lower is 0.53, and our upper, since it continues to the right, will be 10. And now we'll just put that into our calculator. put 0.53 and 10. Calculate. 0.298, and there'll be a 1. 2.981. Okay, and so that about a 30% chance that p hat is at least this large for the sample size. Okay. So that one, like I said, series of fill in the blank. There's like 5 different things here to fill in the blank for, but we went over every single one of those, so hopefully that's okay. Any questions there? In the title of the document, I said skip 7, so we'll go right to 8. We did not talk about how to do 7, so there's no way that we could do it. Okay. Total plasma volume is important in determining the required plasma component in blood replacement therapy for a person undergoing surgery. Plasma volume is influenced by the overall health and physical activity of an individual. Suppose that a random sample of 45 firefighters are tested and that they have a plasma volume sample mean of 37.5 milliliters per kilogram with population standard deviation 7.5 milliliters per kilogram. Create a 90% confidence interval for the population mean of the blood plasma volume in male firefighters. Why did I say male firefighters instead of firemen? Anyway. Actually, there's probably... yeah, anyway. Sorry, I'm arguing semantics with myself. So, when you teach alone for like 8 months, you start talking to yourself quite a bit. So, picking out the key data here, we know our sample size is 45, and our sample mean, 37.5. We have a population standard deviation 7.5, and we want to create a 90% confidence interval. All of that stuff is relevant here. So let's write that down. Sample size is 45. Sample mean is 37.5. Sigma, this is our population standard deviation, 7.5. And we want a 90% confidence interval. Okay. So that's all of our data. Now, whenever we're doing a confidence interval, and this is what we talked about just last Thursday, actually. Whenever we're working with a confidence interval, whether or not we know the value of sigma is a huge component of this, because it affects how we find our margin of error. If we actually know the value of sigma, we end up with a smaller margin of error than if we don't know sigma. Now, if you go to our formula page, we don't need that one, we need this one. Confidence interval for means. So our point estimate is x bar. We've already been given that value. We have to calculate the margin of error. In this case, If sigma is known, then we can use this formula for margin of error, and if sigma is unknown, we have this other formula for margin of error. So it's really a matter of which one do we have. Now, in this case, sigma, remember, is the population standard deviation, so we'll use it here. If we don't have sigma, we'll use S, the sample standard deviation, in its place. So really we're looking for whether we have a population standard deviation or if we have a sample standard deviation. And whichever one of those two things that we have will tell us which of these error terms to use. Okay. Now largely the formulas are the same, but really the difference is in this first term. Here we have z alpha over 2, and here we have t alpha over 2. You see, for z alpha over 2, we have very clear-cut values depending on the level of confidence what we can use for that value. But the margin of error if sigma is unknown, t alpha over 2 is based on degrees of freedom, and the level of confidence which is on the next page. Okay, and that's this table that we looked at last time. We'll talk about that in a moment, because in this case, you can see the keyword here. We know the population standard deviation is 7.5. So we're going to use this first formula since we actually know the value of sigma. So E is z alpha over 2 times sigma divided by square root of n. Okay. Now, notice we are looking for a 90% confidence interval. For 90% confidence, z alpha over 2 is 1.645. Okay. So we'll use that value for z alpha over 2. You can write that as lowercase a if you prefer, if you don't want to write alpha. Alpha is kind of like a cursive a. Anyway. I draw it more like a fish. Anyway, so we have E is z alpha over 2, so 1.645, times sigma, which is 7.5, and then divided by the square root of n, square root of 45. Oops. So we take 1.645, that'll be times 7.5, and then divided by the square root of 45. So we get a value of 1.83916, etc. Now, in the instructions or in the test, when you go to fill in the blank here, I'll specifically say on this problem, round to 1 decimal place. So 1 decimal place will just be 1.8. Basically rounding to the same level that our information is provided at. We could go one space further if we want to do 1.84. That might be a little bit more accurate. But basically just follow the instructions in the exam. It'll tell you exactly how far to round these specific numbers that we're filling in the blanks here. Z, remember, is always to 2 decimal places, but you know, for these problems, we'll specify just for clarity's sake, and the fact that we're letting the computer grade it and compare it against the number I've entered. So more than likely, I've entered a couple of different values depending on how you round, but better to do it correctly. Okay, so we get E is 1.8. So finally, how do we find the confidence interval? Well, our formula for a confidence interval is x bar minus E and x bar plus E. So x bar 37.5, E is 1.8 as we found. So we'll plug those into both places. And so we end up subtracting there, so that'll be 35.7, and this will be 39.3. Okay. Now in the problem, in the exam on the Canvas quiz, that's what I'm trying to say, I'll prompt you to find, I'll go ahead and have you list x bar, just to pick it out of the question correctly, I guess. I'll have you enter the value for E, and then I'll have you enter the two values here for the confidence interval. So in this case, we're establishing that the mean mu is between these two numbers. Okay. Now, what I've also done here is, remember when we did this on Thursday last week, we said it's important that we write a sentence to kind of summarize and interpret what exactly we've discovered by this process. And so I've created a follow-up question to this one where we want to, it's basically set up as an essay question, but we just really only need one sentence. But you know, write a sentence that interprets the result from the previous question. And so we want to write something like this. We are 90% confident that the mean amount, so let me go back to the problem. We want to make sure we reference the actual problem at this stage. We're talking about total plasma volume. So the mean blood plasma volume in firefighters. So again, we're referencing what it is we're actually trying to find by looking at this question. And we've determined it's between 35.7 milliliters per kilogram, incorporating the units of measure that are also given in the problem, and 39.3 milliliters per kilogram. So something like that will be very sufficient. We mentioned the level of confidence, we mentioned what we're actually trying to find, which is the mean amount of blood plasma volume, specifically in firefighters, and then the two values that we discovered. So those four things all need to be in the sentence. So however you want to craft it is fine, as long as we include all that information. Okay? You can even make it two sentences if you want. We're not being picky, we just want to convey the information. That's the main thing. And that's part of statistics, is being able to not only find results, but also be able to describe our results, or what does this mean to anyone that happens to be our audience in this case. Okay, and so problem 9 will be very similar to that, in that it's broken up into two questions. One where we find all the things, and the second one where we write our sentence summary. Okay, now we're making good time. In a random sample of 30 felons convicted of aggravated assault, the sample mean of length of sentencing was found to be 54 months, with a sample standard deviation of 8 months. Create a 95% confidence interval for the mean length of sentencing for an aggravated assault conviction. So we have our sample size 30, sample mean 54 months, sample standard deviation 8 months, and we have 95% confidence interval. So all the data is pretty much here. It's very easily seen. It's not hiding or anything. Let's write those things down. So sample is 30. Sample mean x bar is 54. Sample standard deviation, so that's S, is 8. And we want a 95% confidence interval. Now this is the more likely scenario, that we actually have S, but we do not have sigma. This is what's a lot more likely to happen in actual research. Very rarely do we know population level data. What we're really trying to do is make predictions about population level data, and we want to find what mu should be between based on our research here. Okay, and that's our ultimate goal. So the fact that we don't have any population numbers, that we just have sample mean and sample standard deviation, that's pretty much expected in real statistics and practice. Okay. Unless we're working with a very well-known population. Now, in that case, if we know the population standard deviation, it's very likely we know the population mean already, and there's no point in doing this research. So this is the more likely of the two scenarios, but I wanted to go ahead and ask both because the process is a little bit different in each of these. Anyway, so because we only have the sample standard deviation, we have a little bit different formula, if you recall, for margin of error. And that's this one where sigma is unknown. So we know the value of S. We don't know what sigma is. Sigma is again the population standard deviation, and S is the sample standard deviation. So E in this case would be T alpha over 2 times S divided by square root of n. T alpha over 2 is based on degrees of freedom, which is n minus 1, and the level of confidence, which in this case we'll use 95%. And we'll use the table on the next page to discover this. So degrees of freedom is n minus 1 minus 1, which in this case is 29. Sorry. So we know 95% confidence, we know degrees of freedom is 91. Let's go to this table now. Now on the top I've written the level of confidence, 95%. Let me zoom in a little bit. I'll arrange it so 95% is on the right edge here, and then we'll just go down to 29 on the left side, 29, then go across. We get a value of 2.045. Okay. So we find our degrees of freedom on the left side. We go across the top, we get our confidence interval right there. And so we come down to 29 and across, we get 2.045. That's what we use for T alpha over 2. Now, if you use the wrong method here, then we'll certainly get the wrong answer at this stage. So if you use if you think we have sigma instead of actually having s like we do, then it gives you the wrong answer. So just keep that in mind. Okay, so our error term, or margin of error, is t alpha over 2 times s divided by square root of n. So we use 2.045 times s is 8, and divided by the square root of n, which is 30. Don't forget the 0. Times 8 divided by square root 30. Okay. Now in this case, our data is whole numbers, so we'll actually round to a whole number, which is pretty close to 3 anyway. So we'll use 3 as our margin of error. Alright, so then we have x bar minus e, comma, x bar plus e. So it'll be 54 minus 3, and then 54 plus 3, which gives us an interval 51 to 57. My dog's going crazy in the other room. So. Anyway, I think the mailman showed up. Alright, so we have an interval of 51 to 57. So again, we want to, and so that answers this question, but again, in the next question on the test, I'll have you follow this up with a statement regarding the interpretation of this answer. Like, what does this actually tell us that we got 51 and 57? So again, we are 95% confident that the mean length of sentencing for aggravated assault is between 51 and 57 months. There we go. Each of these problems are worth an equal amount, but what I've done here is I split this up into two parts, but the sum of these two parts is equal to any of the other problems. So I think what I did is all the problems are 12 points on the test, and this one I split up into like 10 and 2 or something like that, 9 and 3, I forget what it was. So you'll probably see it when you go into the test. Do you all have any questions or anything? Okay. So far, good. Well, I hope you all have a good Thanksgiving, and I encourage you to try to do this test before Thanksgiving while it's still fresh. But again, you have the option of waiting through next week. The test will run through Wednesday evening, so we don't have class on Tuesday after Thanksgiving, just on Thursday. And again, next week I think our schedule will be on Thursday. We'll go over Chapter 10 material, and I think we'll have a special session on Friday where I go over the review problems. But I'll make sure I get those uploaded for y'all. So that's kind of what we're looking at there. And that should get us through everything that we need. Not quite everything. There's going to be like one problem in the final that we won't be able to do, but I'll just give you credit for it regardless. But all in all, I feel like we've done a good job getting through everything. The test will close Wednesday next week at 11:59 p.m. So that'll be actually December 2nd. What is that? Yes, December 2nd. Anyway, so you all take care, and good luck with this, and enjoy the time off. Hopefully you have time off from work as well, and you can just relax for a few days. That'd be great. Regardless of whether you're taking the test or not, just don't sweat it and just chill. I think it'll be good for all of us. So anyway, you have a good day, and we'll meet again next week. We're almost done with this thing. We'll get through this.